I'm here with Erik Michaud, and we were at a party yesterday, and I asked him if he wanted to do like an interview hiking, and he said yes. So Erik, who are you?
Yeah, I'm a PhD student at MIT in Max Tegmark's group, and I think about what neural networks do, what they learn, and why they work well, and this sort of thing.
And today we're going to be talking about Grokking and Quanta
scaling and that sort of thing. Yeah.
Can you just like give like a few words on like what you're interested in your research?
So I guess like the most interesting thing to maybe talk about today is like this paper from me and our group called the Quantization model of neural scaling, and this is basically interested in like what is the difference between what small networks and large networks learn, or just like more generally like what effect does scaling have on like what neural networks learn, and like how should we like think about the difference between small and large networks, and like how does this inform how we might try to do mechanistic interpretability, or like what are the sort of like right objects of SETI when trying to understand the networks mechanistically. And we could also talk about Grokking. I was just a middle author on some papers on Grokking from our group last year.
So you prefer to talk about like papers where you're the first author?
We could talk a little bit about Grokking too.
Right.
There's something like kind of related, I think, between like the Grokking stuff and some of the scaling stuff.
Do you have like any pitch for like how this helps making sure we're alive in at the end of the century?
Yeah, so I guess like part of the risk maybe from advanced AI systems is like that or really like it arises from the fact that we maybe don't understand like the internals of the models very well, and if we could like really deeply rigorously understand like mechanistically the computations happening in the model, and ideally eventually who knows, like understand how it reasons about various things like deception and this kind of thing, then you might be able to avoid some of the sort of like worst case maybe alignment failures. So I don't know, I'm just generally hopeful that like if we had a much more rigorous understanding of neural networks, that like we would be in a much better position. This is a little bit risky because like you also might discover something that like accelerates things. But I don't know, I feel like on net, it just feels like really potentially quite good to like have a better understanding of the systems. Like, I don't know, it feels, I'm not the first person to like make this kind of comparison, right? But like the kind of engineering is ahead of the science a little bit, like maybe similarly to how people had steam engines and this sort of thing before we had sort of our modern understanding of thermodynamics. And now we have these deep neural networks, and like we sort of are good at the engineering. We maybe observe empirically some of these interesting properties like scaling laws, which maybe point at something principle going on that we could like hope to have a better theory eventually for how to think about the networks. And like it just feels like having that would be very useful for alignment, at least hopefully. Yeah.
And can you give like a few words on like your background? Like how did you came to do this kind of research? Like if you like were doing physics before, or like when you got interested in maybe like doing this kind of research, if you like decided to help like push AI towards like good outcomes and like decided to do this research, or were you just like generally interested in like deep learning and found this kind of work like useful and interesting?
So I kind of did a bunch of different things as an undergrad. So I was an undergrad just down the hills here in Berkeley, and I was a math major, but like I took a bunch of CS and physics, and during undergrad I wasn't just doing AI stuff. Like for a while I worked with SETI astronomers, like doing radio astronomy, looking for aliens and this kind of thing. And I worked with...
Are there any aliens out there?
I didn't see any.
Is Robert Hansen right?
I don't really have like very sophisticated takes on grabby aliens or this kind of thing, but like it actually does feel like it's tough to work in SETI. Like it was really fun, and like the people are great. You have to have like kind of a good sense of humor, I think, to do it. But it's a little bit tricky because you could potentially spend your whole life searching and never find anything. And like maybe that's the most likely thing, is that you might not find anything.
Maybe it's the same with trying to interpret neural networks. You might not find anything after looking for decades.
Even hopefully not. But anyway, yeah. So I worked with SETI people, and like I worked with this neuroscientist Erik Hoel doing this thing. That it did involve deep learning. It was sort of this information theory type like thing we were measuring in neural networks. But I guess my sort of first like introduction to the kind of AI alignment folks was when I interned at Chai with Adam Gleave, and I think it was kind of a slow build towards doing that. So like I'd sort of been aware of like some of these concerns for a while. I had read like Life 3.0, for instance, as a freshman in college, and now Max, the author, is my advisor, which is kind of fun. Yeah, I just kind of slowly like became more aware of these kinds of things, and it just kind of like fit well with my interests. Maybe I'll just like say a little bit about what I've been thinking about a little bit lately. I don't know. It kind of feels like there's not an obvious answer to like what the right things to look at within the network are when trying to understand it mechanistically or something. So like people try to like there's this recent paper from OpenAI trying to do automated interpretability on like the neurons of GPT-2, and yeah, it just maybe seems like a lot of the neurons like are not super interpretable or something. And like maybe if you looked at something else like I don't know exactly what this would be, but like combinations of the neurons, like if superposition is going on or this kind of thing, like they're interested in like the one possible explanation for the polysemanticity of neurons. So like many neurons in networks like maybe activate in like lots of different circumstances, and so it's like you might hope to, like for each neuron to be like very specific to like some particular type of input or something that like it responds to something very particular, but maybe like in general a bunch of neurons are more messy and like they respond to lots of different things. And like one reason why this could be the case is like superposition, where there's like more features than there are like orthogonal directions in the activation space, and so it sort of has to place the features in a way such that like they're not orthogonal, and this can lead to polysemanticity. But I don't know, it feels like there's also this maybe kind of analogy to the brain or something where like you have neurons, and like what are the right things to look at within the brain? Like you could try to like look at individual neurons, but you could also look at like groups of neurons or groups of neurons, and it's like, well, what is like the like level of abstraction there that is going to like have the most information about like the things that you care about or the dynamics of the system? And like I wonder if there's kind of a similar kind of thing that you could ask about deep neural networks.
Yeah, I guess like some of the work has been on like building circuits and like higher structures that can like represent like simple functions, right? And I feel like this is like the group of neurons that you're talking about is like more like circuits and that like do like specific things.
Yeah. So some of the language here, I'm like familiar with it from this theoretical neuroscientist Erik Hoel, where like for a time he was sort of interested in like what is the like functional unit of the brain, and you might like wonder like, well, what is like the functional unit of a deep neural network, and like yeah, like what is the right thing to look at if you want to understand it, and like maybe something like circuits. I don't have like a super like precise definition of like what a circuit is, but like it feels like that might be more meaningful because it's like the sort of collection of things which together implement some specific computation, and like individually it like might not make a lot of sense, but like the computation implemented as a whole by like that subpart of the system like might like seem to make sense or something, but I don't know.
Yeah, when you look at the computation implemented by the networks, you look at the like floating point like arithmetic, or what's the kind of like way you're thinking about this thing? I think I know in your paper on with Quanta, you talk about like things being discrete. So I'm kind of like curious, what do you mean by discrete in these kind of scenarios? When everything is like floating point arithmetic.
Yeah, okay, that's a great question. Yeah, so I guess like maybe there are a couple like high level models you could have for like thinking about what neural networks like are doing and like what they consist of, and like maybe there's one model which is that like, oh, it's just kind of performing this like generic function approximation. Like there's some manifold that the data lives on, and then the network is just sort of approximating some function defined on this manifold, and like bigger networks sort of globally approximate this function with like greater resolution. And there's sort of maybe this other view of neural networks, which maybe sees them as like collections of algorithms or something, like collections of these circuits, these mechanisms, which perform specialized computations. So like maybe an example of like something that feels more discrete, like an algorithm in the network, is like sort of the circuit that does induction. So like one thing that language models are really good at is if there's some text in their context where like there's some sequence like ABC, and then like at the end of the context, you're predicting the next token, and the last two tokens in the context are A, B, then like they're pretty good at like saying that C is going to come after that. And this is not like a kind of thing that's purely learned over the course of like training in the sense of like bigram or trigram type statistics, but like sort of maybe no matter what the context is, they're able to like do this copying. And it seems like, or at least like as reported from this paper from Anthropic, that like the way that this capability kind of like emerges in the model is more in this like phase transition type way, where like there's some period in the training process where like this capability is not relevantly present, and then like there's a sort of a transition, and then like for the rest of training, like it is relatively relevantly present in the model. And so this is kind of like maybe pointing towards a kind of discreteness where it's like, even if the underlying dynamics is like this like smooth like walk around the parameter space, like in terms of the like, you know, net effect of, you know, like whether the right parameters are like configured in the right way, and like can almost like coordinate with each other in this sort of multi like part algorithm, like that is either present or like not, roughly. Now it's a little bit tricky because it's not like fundamentally discrete. Like as you could imagine, like for any one of these types of like phase transitions probably, which arise out of like this like smooth training process, you can imagine defining a progress measure, like we're just like, what is the distance from your like current place in parameters in parameter space to like a place that would like implement the algorithm, and you could just watch that distance like decrease over training. But at least like maybe from the perspective of the loss, like there's maybe in practice only like a short window in which it's like only kind of present or something, and like for most of like the time it's either not or it is. And like this is kind of what we mean when we talk about like discreteness in our paper.
Cool. Yeah. Thank you very much. This was Erik Michaud after literally like 1 mile of hiking. We'll go more into details of your papers in the next few hours. So I'm here with Erik Michaud, and as you can see, there's some cows in the background that are looking at us. And Erik, I still don't really understand your Quanta paper. So what's the name of the paper and the one tweet summary?
Yeah, so the name of the paper is The Quantization Model of Neural Scaling. And the one tweet summary is that it's possible for smooth loss curves on average to average over lots of like small discrete like phase changes in the network performance. Like what if there were like a bunch of things that like you need to learn to do prediction well in something like language? And so like these things could be like pieces of knowledge or like different abilities to perform certain types of specific computations. So we can imagine like enumerating this like set of like things that you need to learn to do prediction well. And we call these like the quanta of the prediction problem. And then what if the frequency in natural data that like these were useful, each of these quanta, each of these like pieces of knowledge or computational ability, what if the frequency that they were useful for prediction followed a power law?
What's that power law?
So power law is like that the probability or something that something occurs, or like the probability that a given one of these quanta is going to be useful for prediction on a given sample, is going to be proportional to like n to the minus alpha or something. So basically it like drops off in this way where it's like 1 over n to the something.
And like if you look at the scaling curve, when you have this like Poirot law, it's like a straight line on a plot.
Right. So like the famous like scale is all you need plots are a log-log plot, and they show power laws, a straight line in the log-log plot for compute data and parameters.
And when you talk about the like things that are like useful to predict, if you give like concrete examples, those are like predicting like a certain token in some kind of like language modeling task, right? Those are like there's like specific tasks that the model learn or doesn't learn, right?
Yeah, so if you think about like what is required to do prediction well in natural language and like predict the next token in a document across documents on the internet, there are like a huge number of like different things that you need to know as a language model in order to be able to do this well. Where like if you're doing prediction or something in like a news article that appeared on the internet, and like it states some fact, then like in order to predict like certain words in the sentence that like state the fact, then like the language model like kind of needs to like know that fact.
Like the president of the United States in 2020 was ... or
yeah.
And so basically your subtask is like where the model like knows this like specific knowledge, and then there's like more like reasoning task or like mathematical task, like those kind of like Quanta as well, or
yeah, so like in the paper we tried to like actually enumerate what some of these are for like language modeling, and we did this by like clustering together samples based on like whether the model's gradient was like similar for those samples. And like the clusters you get, like some of them are junk, but like many of them are like quite interesting. Where like
what do you mean like having a similar gradient?
Yeah, so like you just evaluate for a given sample like the model's cross-entropy loss and like predicting. So a sample here is like predicting a token from some context from some document on the internet. And you can just look at like the model's cross-entropy loss and predicting this token and backpropagate like gradients throughout the model parameters. And you have basically this big like gradient vector for like the model's like the gradient of the model's like loss with respect to its parameters. And basically you just like want to like find or you want to group together parameters, or rather like group together samples where these gradients are like pointed in similar directions in this like very high dimensional space. We happen to use this like spectral clustering approach to doing this, where we like compute this like cosine similarity between the gradient vectors for like all pairs of samples, which is like fairly expensive. But like the clusters that you get are like sometimes like fairly interesting. It was for a fairly small language model, so they're not like super sophisticated, but things like predicting like a new line at the end of some line of text within a document where the line lengths are limited. So it's like the model, in order to like predict the new line, has to sort of like count line lengths for the previous lines in the document, and then like it's able to like use that to like accurately predict when like a new line should be present. And like you can like find like just a large number of like clusters where the thing that is common between the clusters just seems to be that like it's the same like type of problem, or like doing prediction on those samples like requires the same piece of knowledge, and so like you might call like these the quanta, or like evidence of like there being quanta, although it's like a little bit tricky because like we like in doing the clustering like kind of enforce this like discreteness where like everything is a member of a cluster, like a particular cluster and not another cluster. So anyway, it's like complicated and weird, and like who knows like whether like this is like even like the right model for thinking about the networks. But like it would be very exciting like if it was like the true model, because it would maybe tell you like that there were these like set of things where like if you enumerated them you could like understand the network's performance, and like understood you could understand like what it has learned. It's just like there's like this like set of like pieces of knowledge or pieces of computation that are needed, and you could describe what these are. You could like find them in the network and like maybe hope to mechanistically understand the whole network by decomposing it into how it implements each one of these things, how it learns each piece of knowledge or each piece of computation.
You said you tried on like smaller models. What kind of like models are we talking about? Like what kind of size are we talking about?
Yeah, so I was using the Pythia models from Eleuther. So they range from like 70 million to 12 billion parameters. I was just going up to like the second to last, like the 6 billion parameter model.
So what kind of like experiment you run? So you did like the clustering, all of these things, and you showed it like there's a like new line token. There's like maybe like other tokens. You have like example of like other like simple prediction things that you can where like you like observe like the subtasks being like learned at some point. Like other like specific examples of subtasks.
Yeah, I mean, so you can like look for tokens for which the scaling curves are sharp. So like you can like look I have these models of different scale trained by Eleuther, and like I can evaluate them on a large number of tokens. So I have a large number of loss values, and then you can just like look at each one of these like individual loss curves. So like you can look at like the loss as a function of model scale, the number of model parameters, and like you have this scaling curve, and like we know that like the average of like all of these scaling curves for like many different, like all the tokens like in the corpus or something looks like a power law, but like, do they individually look like power laws? And like you see kind of like a range of different behaviors, at least like with like the seeds of the model that are released. And you can find like, you can find like individual curves which look like the loss is high and then it like drops to like approximately 0 at a given scale. And it's like, oh yeah, maybe like in general these seem more like tokens that involve like facts, whereas like things that look really smooth, like it's not clear that there's like a specific like piece of knowledge that like you could have to like do prediction well at all, but it might just be like based on more like intuition or heuristics or like many heuristics that might be contributing altogether.
Yeah, I was wondering if you asked like how many tokens are we talking about? Like, are we talking about there's like number of tokens for the byte pairing like encoding from OpenAI, or is it like thousands of tokens?
So
you like
yeah,
them like individually or?
Well, so there's a little bit of like this like notational overload thing where like you can talk about like tokens in the vocabulary, but you can also talk about like tokens in documents.
Right.
So there's like 50,000 like tokens in the like vocabulary of the tokenizer or whatever. But like across like a large number of documents, like in the pile, the data set that the models were trained on, there's like a test set which has like a few 100,000 documents, I think. And so it has like definitely over 100 million tokens. And so like you can imagine like computing like a loss or like a scaling curve on like each one of those like 100 million tokens.
And so the clustering you did is like automatic, right? So you didn't like force the model to like you didn't force a cluster on like this like new line thing. You just like made this cluster automatically, and then you like look at the different clusters. How many clusters did you find like in total? Approximately.
Yeah, so when I did this in the paper, I used like 10,000 samples, like 10,000 tokens where like the model got like low loss on, and then like I think I was mostly looking at like an experiment where I like produced 400 clusters, but like this is a little bit tricky where like the algorithm like has to put everything in a cluster. So like there are a bunch of clusters which like are low quality, and then like a bunch of them which are much higher quality. Like I don't know, like this is kind of a cool exercise, maybe like it may be useful for mechanistic interpretability, because like the sort of end result of this is like, okay, well maybe we have like 200 clusters or something of like model behaviors where it's like, yes, like each of these like samples involved like the model was like really good at predicting this token from its context, and like maybe it was like really good at predicting that token from its context for like similar reasons within the cluster, and then you could hope to like fight a circuit or something for each like cluster of behavior.
From reading your thread about Quanta, you mentioned something about the frequency of some words in the training data set, and also something about like number of parameters frequency. So yeah, I don't really understand exactly what's this whole deal about.
Yeah, so like the kind of core hypothesis like of the model that we make in the paper, in addition to like there being this discreteness or like this discrete set of things you need to learn, we also assume that there's this power law governing like how useful these things are for prediction. So you can imagine like there are some facts, like I don't know, like Max Tegmark is a physicist at blank, where like there's some frequency that like knowing this like piece of knowledge is like useful for prediction, like one in a million or like 1 in a billion, next like word prediction problems like on the internet require this piece of knowledge, and then like maybe there's some other like much more frequently useful like pieces of knowledge if you're going to do like language modeling, like understanding basic grammar or this kind of thing would be like if you could only learn so many things, you should probably learn the basic grammatical rules before you learn anything about who Max Tegmark is.
So you say like you have like a very small model that can like only like shift like 1 million parameters. It doesn't have the like size to like remember like who Michael or like Erik Michaud is. But if it's like a 1 trillion parameter model, then maybe you must like remember all these facts. And so like there's like an ordering in the like quanta you learn, and you like start by like the quanta like the most useful for your training.
Yeah. Like if you could only learn so many of these things, you should learn the ones which like reduce the mean loss the most. And these are the things like we sort of conjecture that are like most frequently useful for prediction. So like the most frequently useful pieces of knowledge maybe will be learned by the small networks, and then the big networks will like have circuits, or like they'll know the knowledge that is like much more niche, like niche physics or like niche facts, which smaller models just like don't have the capacity to learn.
Yeah, do you have like any like empirical evidence for this? Like have you like done experiments, or just like a conjecture on like what do you think your like theory might predict?
So when we did the clustering of the samples in language, you could look at like the size of the clusters and then ask whether like the cluster sizes drop off as a power law.
Yeah. How do you measure the size? Like number of things inside, or like the distance in some like space?
No, yeah. What we did was we just looked at like the number of samples in each cluster. So we just like randomly, we did some filtering, but like basically we just like took a bunch of samples, which the model got low loss on, and clustered them, and then looked at the size of the clusters. And like this is like really messy, and like there are a bunch of reasons why like even if there was a power law, this could fail. But like I don't know, like it was a pretty messy curve if you look at like the size of the clusters like versus their like their ordering by size. But like maybe eventually it kind of looks like roughly power law like, and like very roughly with like the exponent that like we would sort of expect from the like empirical scaling laws for the language models themselves.
So what's a power law? Is like a power law in the number of items in your cluster?
Yeah. So like cluster 100 has like I don't know, like 50 elements, and then cluster 200 has like 20 elements, and like the size of these clusters will drop off if you put it on like a log scale of the size of the cluster versus like the sort of ranking of the cluster. Once you order them all by size, then like eventually it looks like a straight line, maybe roughly, but it's like a very tentative result.
And so like when you talk about like cluster at the beginning for like grammar stuff, the cluster will be like the rules of like I am, you are, or like the S at the end of like verbs or something.
No, yeah, there like really are like clusters like that like we find by doing this. So like there's a cluster for like when you have like something like DON apostrophe, then like it predicts T after that for don't. And like there's just like a huge number of examples like this. Like commas after the word however is like another one of the clusters. And so it's like, well, like knowing that like commas often come after the word however is just like it turns out is like very frequently useful for like predicting the next token in like internet text. And so it's like something that even the small language models like it's a piece of knowledge, or like what we would call a quantum, that like even the small language models possess.
So yeah, if I was like someone on YouTube that like disliked everything I watched, and I was like posting like an angry comment, I would say like, yes, your theory seems kind of nice, but it's just like putting like a nice name like Quanta on things. And I feel like everything can be like described as a quanta if you really like think hard enough about it. And I really don't like see like anything that like new that your like model predicts. I don't really like like gets like why that's useful to think about. Yeah, do you have like anything to say to those people?
Yeah. So I guess like there are a lot of ways in which like this like model could like not actually describe what's going on in language models or like real neural networks. I guess I could say this. So there are like other models of where power laws come from, like where scaling laws come from for neural networks. And like they say that like for instance, the like exponent governing like the power law comes from like the dimension of like some data manifold, some manifold that the data lies on. And like we're just saying that like, oh, maybe it comes from this like power law distribution over like the frequencies that these things are useful, these quanta. One of the things that we do in the paper is we like construct data where like our sort of story of scaling is true, where like smooth power laws really do like average over lots of these like phase change type things. And there are these like discrete sort of subtasks in the prediction problem. And so it's sort of possible, like, I don't know, I think the interesting point that the paper makes is that it's possible for this type of story to still like give rise to what we observe with power law scaling, and that it's possible for data with the right structure for this to be the right story. And then it's sort of still an open question whether like language data has this kind of structure, whether it's like more sensible to think about the problem of predicting language as this kind of like smooth interpolation type of thing versus like a bunch of like discrete pieces of knowledge or algorithms kind of story. And I'm not really sure like which one is right, but at least I think it's maybe useful to have a counterpoint to the sort of everything is smooth type story.
So basically, you're saying that like you can explain things in the scaling laws pretty easily with your model, and for some stuff in language modeling, you can explain it with Quanta, and is it basically right? So scaling, you're pretty sure that it explains a lot of things that is like already like explained by like other papers, and like in language modeling, you're like explaining some stuff.
So one thing we do is that like our model makes this like kind of prediction about like what the relationship between the data and parameter scaling exponents, and like some models, other models would maybe say that like the data scaling exponent and the parameter scaling exponent like should be the same. One of the things we did in the appendix of the paper is we like plotted for like a bunch of other papers that have done empirical studies of neural scaling, what they've like measured the parameter scaling exponent as and the data scaling exponent. And like frankly, the points are like all over the figure. It's like a total mess. The like chinchilla scaling law like place in the figure where that point is in this like plane of data parameter scaling and parameter scaling exponents is it's like right in between like the theory line from like other models and our model. So it's pretty ambiguous at this point what is like correct.
So are you saying that maybe the experiments in chinchilla don't fit with your like with your experiments or your theory?
No, so I guess like we would expect that like the data scaling exponent is going to be less than the parameter scaling exponent, and this is like indeed what they observed in like the chinchilla scaling law study. So it seems like somewhat encouraging, but like if you actually look at like the precise value of like what these like scaling exponents are, it's sort of like not exactly what we would predict. So it's sort of like in the right direction, but like not like precisely like what we would expect. Yeah,
right. It's in the right direction, but not exactly what we would like.
Yeah, and then other studies are just like totally different. So like with OpenAI original like Kaplan study, it was like the opposite, where it was like sort of like the data scaling was like steeper or something than the parameter scaling. And then like there are a bunch of other sort of like vision maybe paper like data points on the figure, and most of these are like below the line where like the scaling exponents are the same, which is like encouraging for like our theory. But then like there are a bunch of like there are other points also which like are above it, and so like overall it seems like things are messier than I would have expected, like with like neural scaling in the wild.
And just to be clear, when you talk about like scaling exponents for parameters and like data set size, etc., we're talking about like the sharpness of the straight line in the log plot, right?
Yeah, it's the slope of the power law in the log plot.
I think now I've like kind of get your paper. Is there anything else you think is important?
Yeah, so I guess I'd just say that like I thought this was like useful to put out because like if it was true, then like it would be very exciting because it would sort of, I don't know, sort of like a first shot at like a paradigm or something for like a science of deep learning where like like what if like there are like these like things that like we could like understand the network's performance by like reference to just like whether or not it learns these things, and like we can understand scaling as just being a matter of like learning more of these things, or the process of training as just learning more and more of these things. And if this was true, then like hopefully we could mechanistically understand the networks by enumerating like what these quanta are. But like in practice, I expect things to be like probably a little bit trickier than like even like than at least like the theory like laid out in the paper.
So maybe the discovery of the quanta in scaling is triggers a new field of quantum interpretability. I'm very excited about this. Maybe we'll talk more about some other stuff you worked on, like Grokking, in the next 20 minutes of hike. See you in the next build. So Erik, this is maybe like the last shot of the vlog. I met you at NeurIPS on Grokking, and you keep doing those like talks about Grokking, and I think it's like worth talking about a little bit. And recently, I think you've been publishing like 2 papers on Grokking at iClear.
One at NeurIPS and one at iClear.
Yeah, so do you want to just like explain quickly like what's Grokking so that our viewers can like Grokking?
Sure. So Grokking is this phenomenon where neural networks can generalize long after they first overfit their training data. This was first discovered by some folks at OpenAI. Basically, they were training small transformer models to learn these basic like math operations, like train the network to do like modular addition or something. And you only see like some fraction of all possible pairs of inputs or something. When they train the networks on this task, they would first completely memorize the training data, like the pairs of examples that they saw, and like they would not generalize at all to like unseen examples. But if they like kept training the network for like way longer than it took for the network to overfit, eventually the network would generalize. So this is just like a surprising like thing to observe in neural networks. Like they perfectly like fit the training data, and then like somehow like you keep training, and eventually they switch over to doing something else internally, which like actually allows them to generalize.
Because like in normal deep learning, when your network like has like very very low train loss and very high test loss, is because like it's like overfit, right? And so like normally you're like stuck, but like in this case it's like if you like wait long enough,
right,
it works. And I think this I was like listening to like Neil Nanda talk with Lawrence Chan on their work on Grokking, and they were saying that like this is kind of different from double descent. Like is there a sense in which like Grokking is when you like have like a small data set and you like go through it like many times, and double descent is like more when you like go through like your entire data set, and at one point it will like generalize?
So I'm not actually super clear right now on like the distinction between like Grokking and double descent and like the exact setup there. There is this like paper from some folks at Cambridge on like unifying Grokking and double descent, and so like maybe these things are kind of two sides of the same coin. I think overall like there's some message here about there being like different mechanisms that the network can use to like fit the training data, and like maybe these are like learned at different rates and like incentivized in different amounts over the training process, and this can like lead to some like wonky training dynamics where there's like more than one thing happening inside the network during the training process. Yeah.
So yeah, you've been publishing 2 papers on Grokking recently. Why are you so excited about Grokking, and yeah, what are like the main takes on these papers?
Yeah, so I don't know. Grokking, it's kind of exciting just because it's weird and like surprising. And so like it's just I don't know, like it feels like progress if like we can understand something like in these networks that like surprises us, and often like things that surprise us are like good like targets of like if we can understand these things, then maybe like they'll say something more general. So I don't know, like what is like more general, like what is to be learned in general about grokking. So there's a couple things here. In our first paper, we like looked at representation learning and like how sort of generalization in these networks on like the math operations that they're learning depends on the network like learning these like particular like structured representations of their inputs. And like it turns out that like this like structure that we found where like if for instance the network is learning to do modular addition, then it'll like arrange like in some space with the embedding space for small transformers. It'll put the embedding vector for and the embedding vectors for each of the inputs. So like if you're doing addition mod 113 or something, then like there's a vector an embedding for 0 and 1 and 2 all the way up to 112, and it'll sort of like learn eventually to like put these in a circle where it sort of goes from 0, 1 all the way up to 112 and then back to 0, which is sort of exactly how like we visualize like modular addition in terms of clock math. And it seems like maybe the networks learn something similar here.
So is the learning of all these like modular representations happening through Grokking, or is it like independent?
Yeah, so I guess there's like this thing that happens in the network where first it memorizes, and so like quickly the network like finds some way of memorizing, and like I don't really understand like mechanistically how it does this, but like early on in training it memorizes. But then there's this kind of like slower process of forming the like circuit which actually like performs some like very structured computation, which is like equivalent in some way to the operation that the network as a whole is trying to implement. So like if you need to generalize on like modular addition, then like the only way you're going to do that is like if internally you implement an algorithm that does something like modular addition.
And was that something like Neil Nana discovered on Twitter? Was this like modular subtraction addition that was like a sum of cosine and sinus?
Yeah,
the same thing.
Yeah, so like the reason why like we saw, so like we kind of was like, oh yes, there's this like structure here where there's like this ring shape and like how the network is organizing its representations, its embeddings, but we didn't really understand like how this was being used. And then like Neil, like in his description of like how the networks are like fully implementing modular addition, like explained like why we were seeing this, which is it's like kind of the first step in this like multi-step algorithm which like performs this computation, which is like sort of equivalent to modular addition and allows the network to generalize.
So yeah, if people like want to like learn more about this, what's the name of the paper?
Yeah, so the paper on representation learning was called Towards Understanding Grokking, an Effective Theory of Representation Learning. It was an oral at NeurIPS 2022.
And what's the other paper that you presented, like I think at ICLR?
Yeah, so I went to Rwanda to present this paper. It's called Omnigrok, Grokking Beyond Algorithmic Data.
That's such a cool name.
Yeah, so I think so. But both these papers were led by Zimeng Liu's a grad student in the physics department with me, and yeah, Omnigrok is like, yeah, it's a kind of a little bit of a cute name or something. But basically, we just showed in Omnigrok that it was possible to observe this like grokking, this like delayed generalization on tasks that were not just the sort of algorithmic tasks, which was where like grokking was first observed by people on OpenAI. But like we could also observe it on MNIST and sort of like other standard tasks in deep learning. And like basically the way we did this was we just instead of for MNIST, for instance, training on like 50,000 examples, we would train on fewer samples, like maybe 1,000, and then we would initialize the network weights to be really big, and then train with weight decay. And like when you do this, it just like it turns out that like the network will first memorize, and then like you continue training like with weight decay, and eventually network will generalize. So this is like Omni, like we can sort of grok like beyond algorithmic data. We can grok like on anything, maybe or maybe not. But at least a few things we can grok on that are not math operations. Yeah.
From this to everything. Was it the first time like someone showed something like grokking on this?
I think so. Yeah.
Cool. Yeah. If you had like people watching that are like PhDs in deep learning and want to like collaborate with you, like what are like your like lines of research like you might do in the future, or like stuff you're interested in grokking, or interpretability? Like, is there like any special things you might do in the future that you're like, you can share?
No, you know, you should not collaborate with me. No. No. So I don't know. I guess
Everything under NDA.
like what is like the like overarching like kind of like message here?
Yeah.
Like with both like the quanta scaling stuff and with the grokking stuff, like we sort of hope to like identify these like maybe mechanisms in the model that are like responsible for like certain behaviors, or like for the model generalizing. And like in the case of grokking, there's sort of like multiple circuits or like multiple mechanisms that are going on in the model or something, where there's like a memorizing mechanism and a generalizing mechanism. And this is like very like you know, I think maybe this way of thinking was like maybe first put forth by Neil Manda in his blog post on grokking. But you know, you can like imagine like tracking like how this mechanism forms for the generalizing circuit over time. And you know, maybe there's like many copies of the mechanism in the network, and there's just like kind of a lot going on in the network. But you can maybe think about the network as like consisting of some number of these mechanisms which you can imagine enumerating. And like maybe just in general, beyond grokking, but like in large language models and otherwise, we might hope to sort of like decompose their behavior in terms of like a bunch of these mechanisms. And like if you could do this, then you could hope to do interpretability, but maybe other things like mechanistic anomaly detection or something. Like you might hope to you know, eventually be able to say like, yes, when the network did prediction on this problem, it like used like this and this and this mechanism or something, or like these were relevant. And then like maybe there's a mechanism in like sufficiently large language models that like reasons about deception or something. And then you could just like identify it and like identify when it's being used by the model for inference, and like, you know, not worry about sharp left turns or whatever.
Towards Omnigrok and detecting sharp left turns. Thank you, Erik. And yeah, if you want to watch more of the shows, subscribe to my YouTube channel and support me on Patreon, and see you tomorrow for the next video of the Inside View.